Thank you so much for having me. Really excited about the workshop today and all of the talks. And I see audience have joined from all over the world and really excited to present to you. So I will not be able to monitor the chat because I am on my laptop and I don't see the chat when I'm in the presenter mode. So I'll try to address, if somebody wants to unmute amongst the panelists and just inform me of that, that would be helpful. So today I'm going to present mitigating the impact of bias in selection algorithms. This is joint work with my amazing collaborators, Devin Desai, who's a professor of law and ethics at Scheller School of Business, and Jad Salem, who's my amazing graduate student who's led the mathematics and a lot of this work. So before I start, I wanted to give sort of an overview of what our research group has been thinking about in algorithmic fairness through the lens of optimization. I'm an optimizer by training. So we like to dabble into questions about, what is fair, thinking about, if you're giving loans to people in an online learning manner, how should the loans be processed? How should they be given? How do you do profit optimization by changing prices when the demand functions are unknown? And still be fair to customers? How do you place facilities like emergency rooms while having equality of access? And that's one set of questions. Another one is, what is the impact of bias? And we look at, bias data, as Panos was just talking about. So bias data, there's some evaluations, maybe it's not sampling bias, but there's some other kind of bias in the data. And how do we still make decisions on hiring or giving freelancing jobs to people or admissions? And this is the part of work that I'll focus on in this talk. We also think about what is the impact of uncertainty on various operational problems like districting. So that's a districting map of South Fulton City that districts based on 911 calls data. In the service industry, housing markets, how do we account for the impact of uncertainty? And moreover, how do we design algorithms that have some sort of interpretability and explainability embedded into them? So that's sort of an overview. And given the amount of time we have, I'm going to focus on the impact of bias, but I would love to talk about any of these topics offline. So the bias study in this talk is really motivated from this example of hiring in practice, where a series of incidents occurred over the last year. So Microsoft, Wells Fargo, Adidas, Google, Boeing, they all announced major programs to address racial disparities in employment. So they realized in the last 5 years of hiring, they did not promote a lot of African-American managers, senior contributors, and senior leaders in the company. And so they announced that, we are going to have a diverse workforce by 2025. Meanwhile, they were already being sued by the Labor Department for the past 5 years of their hiring practices, and Microsoft had to settle with the Labor Department around $3 million for alleged race discrimination hiring from 2015 to 2018. When these companies again made these claims in the summer of 2020 that they're going to increase racial representation in their top managers, Labor Department again went to investigate, because the question is, how are you going to do that? And your claims don't seem to be about the quality of the candidates, but more about the groups that they come from. And this really gets to the heart of the question we're going to ask today, which is, given that Title VII, which is anti-discrimination laws, specifically state that you cannot use protected attributes for making decisions in regulated domains, such as education, housing, employment, public accommodation, and credit. How are you going to increase representation when you've not been able to do that over the last few years? So there is this tension between disparate impact, which is what happens when you've sort of taken a group blind algorithm, so where you don't account for the race, color, religion, national origin, and so on. But when you look at the impact of your algorithm, that seems disparate, as the reason why Microsoft and other companies were sued by the Labor Department. But if you try to do something and account for these attributes, you end up having disparate treatment, and you don't want to actually treat people differently based on these protected attributes. So the question we're going to think about is, how should an entity like Microsoft fix the underrepresentation in their hiring pipeline without resorting to disparate treatment? And this is given the fact that the data that we see is often biased. There's a lot of study on bias in evaluations data. So that's the problem. And we're going to first model it mathematically, and then we're going to talk about solutions from the mathematics. So here's the outline of the talk. We're going to look at this problem through the lens of what is known as a classical sector tree problem. Don't even get me started on the name of this problem, but that's what it's called in the computer science literature. We're going to look at how do we mathematically model bias, give some algorithms that mathematically make sense, may not legally make sense. And I'll show you an experimental study to sort of drive home the message. And then we're going to look at how does this work with the anti-discrimination laws. Okay. So the online sector tree problem is the following. Let's suppose you want to hire 2 students for a team of a mathematics Olympiad amongst 5 students. So as you see the students, they're going to come up one by one. So it's like a streaming model. I know there are 5 students overall, and I need to make a decision of whether I want to select the student for the math Olympiad, or I want to go on further. At this point, I don't even know if there are more students that have a score of above 90. I don't know whether this is 90%. I don't know what's the maximum score students can have. I don't have any distributional information about what the other student scores could look like. And as students appear, we can make a select or a reject decision. And let's say I selected April and Maya, and then I could see like the sort of the candidates who appear at the end, they might have a higher score. And so this problem has been well studied in computer science. And the question is, suppose your algorithm doesn't know the order of arrival, it doesn't know what is the distribution of scores, how does it still select good candidates? So it sort of tries to capture this trade-off between partial information and full information. And the guarantees are, can you maximize the worst case performance of your algorithm under any set of candidates that could arrive, given that you know what is the total number of candidates. The tricky part, though, which is not being studied in the literature, is, what if these candidates had some other information than the scores that are seen by the algorithm? So what if these students had an extra job while they were preparing for the test? How do you even account for that part-time job? Could they have scored a higher score if they didn't have that? Or in other words, how do you account for the social context? How do you account for things that were external to this test score that were taken? And maybe the test was itself biased and did not actually capture the true ability to perform on the math Olympiad. Or maybe with some extra training, they could have performed much better. And this is sort of a well-established fact that data is biased. We see more and more studies from machine learning, from social sciences, from psychology, that are quantifying, that are sort of qualitatively talking about there is some bias. So there's an experiment. Are Emily and Greg more employable than Lakisha and Jamal? Why does John get more STEM jobs than Jennifer? Gender bias in academic recruitment, hiring algorithms can introduce bias. Well, if evaluation metrics are biased, what can you do about them, right? And Amazon's Scrap Secret AI recruiting tool that showed bias against women. So there's a whole range of work talking about the fact that data is biased. What we are interested in is, what is the impact of this bias? We know data is biased. Can we still design efficient algorithms, whatever that means, and provide some meaningful interventions? Good. Everyone with me? So I'm not claiming that we can completely remove bias. What I'm claiming is maybe we can move a little bit towards the positive direction. And what we want to be careful about is also that we don't want to introduce new biases and make it worse. Right? So mitigating is sort of the word to keep in mind instead of resolving the bias, because I don't think that's possible. Okay. So is it possible to quantify bias? So, okay, now we are talking about the mathematics. We see some score. If somebody had a side gig or a part-time job, should we increase their scores by 5%, 10%? Like, how does it actually translate quantitatively? It's unclear. So it's unclear. People all of these studies that we see on stereotype threats. This is beautiful work by Claude Steele, who was actually handling admissions at Michigan. And he started looking at the performance of African-American students. And he realized that if they were given a test that said, you have to prove that you can do this, then the performance of the stereotype groups was much lower compared to if they were just told, this test is for fun and, we're just learning in this process. So the way the test was posed to the students, that had an impact on the performance. And it was a lower performance, but it doesn't give us the quantitative translation without the bias. So we don't know quantitatively how much bias there is, but maybe we know there is an underestimation and an overestimation. And this was the key idea that John Kleinberg and Manish Raghavan had in 2018, which I thought was so beautiful because it gave us a mathematical model and it sort of moved away from this non-mathematical debate is fairness and ethics issue to really a mathematical problem. So here what's happening is you have candidates who arrive one by one, and this was an offline model. So here, every candidate belongs to one of these groups, G1 to GK. And what the algorithm observes is a biased potential. Every group's members suffer the same amount of bias. So let's say this beta J factor was 5 and the true potential was 100. You would observe only 20 for the candidates for that particular group. So you would observe a scaled potential of the candidates, or the scale utility of the candidates, dependent on their group membership. And this is very interesting. It's a very simple model, but it still gets to some of the key algorithmic design ideas. And that's what I want to get across in this talk, given that this is crossing disciplines, that maybe mathematics can give us some important design ideas that can be used in broader contexts. So the group model of bias was something we also observed in an education data set. So this was SAT scores of different schools in New York City, different high schools in New York City. And we see that the distribution, so we plotted the distribution of SAT scores of students based on whether the school had a high economic need index, which was it was a poorer neighborhood, or it had a low economic need index, which was it was a richer neighborhood. And you see, it's literally a translation in the SAT score distributions. So the bias factor here is something you could maybe estimate from the data within some error. And if you normalize these distributions, it comes out to be 1.25. So just as an example that, yes, at an aggregate level, you might see these trends of bias and you might be able to estimate those. Okay. But what is a limitation of this model is that it assumes the same amount of bias factor for every candidate in that group. And maybe there's no way to sort of compare a 20% student from one group to a 100% student in the other group, right? So it seems like this is a way of a comparison to make. So with that in mind, we introduced a partially ordered set or a Poset model of bias, which says that, irrespective of the groups people come from, given all the information that you have about candidates, up to whatever extent you can model sort of their external factors, maybe there are some pairs that you can compare with certainty. So you can say that, this candidate is definitely better than this candidate. And maybe there are some candidates where we don't know how to make a good comparison. We can't make it with confidence, right? So this structure is mathematically known as a partially ordered set or a Poset. And this was studied as early as 1940s. So it's a very old mathematical structure with beautiful combinatorial properties. And what you see on the slide here is what is known as an interval order. How much time do I have? So
6 minutes.
6 minutes. Wow. Okay. So I need to really speed up. So this is an interval order where I have a score of, I have a scale of score 10 and candidates have some uncertainty. And based on these intervals, there are only some candidates like E1 is definitely better than E2. So we modeled this, and given that our secretary problem became the bias secretary problem, and the question was, can we design algorithms that find something as close to the optimum who knows the unbiased utilities, who knows all of the candidates, and can we still select candidates that are good enough? So that's the question. And we looked at various fairness properties. We want to have equal opportunity for equally qualified people, but how do we know who is equally qualified? And we went over a few ideas like demographic parity, ranked, and so on. Let me not get into those because I want to give you sort of an intuition of how the algorithms work and then go on to the legal aspects. So here, suppose we have 5 group sizes. Let's just work it out. And each has 10 candidates. So we have 5 groups. Each has 10 candidates, and we need to select 6 people. How would you do that? One way you could think about is, I'm going to select one of these groups at random, and I'm just going to pick all the candidates from that group. That seems completely unfair. But in expectation, it'll give you the right mathematical quantity that we're looking for. It'll give you a competitive ratio that's bounded. That's not a good idea because it seems completely unfair. And that goes to the independence property that I did not talk about in the last slide. So other thing you could do is you could say that, well, I'm going to pick one of my favorite groups and select people from that. That's also not good because the bias factors are things that we're assuming are adversarially decided. So if you don't have equal probability of selection from each of the groups, then that already becomes a problem mathematically. So that to me was something that was very interesting about this model because it gives you some sort of a demographic parity, some sort of an equal probability of selection from every group. Otherwise, you can't bound this competitive ratio that I've written on the slide. So the way to do it is very simple. You select approximately 1.2 candidates from each of the groups, and you call it a day. And you try to select the best candidates from each group. Although this is good mathematically, legally this is not good because quotas are illegal. We don't want to actually look at the group membership and look at and select candidates from that. So even mathematically speaking, there is an interesting problem here, which is suppose we know there are total 50 candidates, but we don't know how they're assigned to the different groups. And this mathematical question actually gets us to something that might be usable practically, which is if you didn't know the group sizes, you can't actually parallelize your algorithm for each of the different groups, but you can create sort of fake labels for them. And this is an idea that's very old. It goes back to Jose Soto's work in 2013 for dealing with matroid sector tree problems. And what you do here is, so you have 5 groups, total 50 candidates. You don't know which groups they belong to or what are the sizes of the groups as they come in. What you do is you give them, okay, thank you. You give them a label, and that's a random label. So you assign them to 6 different random interview committees and tell each of those to select the top candidate. And this is really nice. It gives us a bounded competitive ratio of G plus 1. G is sort of the best you can do times E squared, but it also gives us something that's very practically possible. So it gives us something that can actually make an algorithm with having different interview committees that operate independently. So we extended this to the Poset model of bias, and we can do what is known as chain decompositions, and we can select candidates and generalize what we could do for the group setting. These are different ratios, which are in our paper that was published in Vine. And let me quickly talk about the experimental case study. So here we had candidates and we had different data on them. We did a linear regression. We looked at what is their hireability based on their computer programming score. But this learned a skew for female candidates, unfortunately. So that skew for female candidates, if we try to remove it, we don't know, we maybe know the maximum skew, but we don't know what is exactly the range in which we probably know the range, but we don't know exactly how much of the score we should shift. So that gives us a Poset, and that's the Poset that we could use to have a fairer selection process. So in the 2 minutes that I have remaining, I want to talk about this and how this connects to anti-discrimination laws and the Microsoft paradox, as my colleague calls it. So in the so let's say there is a person who is concerned with workforce underrepresentation. The law actually says that it's good to diagnose and document imbalances that operate as potential built-in headwinds for minority groups. So it's good to look into your data. It's good to do what Panos was talking about. It's good to detect bias. And if you think that we just don't get enough good underrepresented minorities, then that is a big issue, and maybe there is a bias that's happening somewhere, and you need to dig into that a little bit more. So the next question might be, maybe there is a bias problem, and constructing intervals or a Poset might be a good idea. So that's what we just discussed. So why a Poset? So this is sort of the key of the legal argument that we're trying to make, and we're trying to refine, that Posets can be constructed in a way that is mathematically justified so that there is due process. What's interesting is that the law doesn't like to treat individuals as numbers. And the case that I'm just going to sort of mention here is Johnson v. Transportation Agency, where you see this thing happen, where there's a man interviewing and a woman interviewing, and they have a difference in the scores. And the man sues because the woman got the promotion over him. So the law doesn't like actually treating people as numbers. And so Posets might actually drive us away from numbers and still be data inspired and be more in line with what the law likes. And they actually don't impose a quota. It really depends on the distribution. So I'm sorry if I went a few seconds over time, but that's the summary. Thank you for listening.